Group and representation of monodromy. Can you hear this? Yes. Huh? So fundamental group and representation of monodromy. So we have fundamental group, pi1 of some space, a base space, and then a representation in something. So what we do today is we make this as simple as possible. The space is just the disk minus the origin. And D is the disk in the complex plane. So that means pi1 becomes very simple. Pi1 is just the group Z. And this is generated by one element by one. So if you wish to compute monodromy, we need to know what is the image of the generator. And what we need to do is we need to produce many examples. And so a main source of this kind of examples is the Milner vibration. The Milnor vibration. That's main source of examples. So what is this Milnor vibration? We start from with the polynomial mapping from Cn plus 1 to C. So this is a polynomial. We make immediately an example. It is the polynomial in two variables. So in the example, n is 1. And it is the polynomial, let's say, x to the power 3 plus y squared as example. So to do Milnor vibration, we ask two things. We ask that f of 0 is 0, just for convenience. We ask that the differential of f at the point 0 is 0. So we need a singular point. And a further assumption to have Milnor vibrations is we assume that the ring, if we take the formal power series in the variables, so x naught, x1 up to xn, and we divide out by the ideal generated by the partial derivatives, so dxif, I take the ideal generated by this, we ask that dimension of this vector space is finite. This is an algebraic condition, but geometrically it just means that 0 is a singular point, because the differential is 0, and that it is an isolated singular point. So all points nearby 0 are not singular points. That means at such a point, the differential of f is non-zero. So basic knowledge is if you have a function and the differential at some point is non-zero, then locally you can precisely describe the level sets of that function by implicit function theorem. So if we work with those hypotheses, we get the following pictures. We have a fiber f equal to 0. We have a singular point, 0. So total space is c to the power n plus 1. But in our example, it is c2. And the picture which I draw here is a real picture. So on the blackboard in my house, we have only two-dimensional blackboards. So we can only draw two-dimensional things. And this is the level set of perhaps I mismatch the conditions here. So when x is positive, so I prefer to write minus y squared. So when x is positive, these are the roots of this point is the root of when we are here at point x here, then y is the square root of x to the power 3, and there are two such square roots, we get this picture. So that's basic example of an isolated singularity. When we compute the differential at some other point, so the x derivative of f in this example is 3x squared, the y derivative of f is 2y, and the zero set where both derivatives vanish is precisely the origin, and all other points, at least one partial derivative is non-zero, so we have an isolated singularity. This is slightly stronger. This allows that we have perhaps singularities far away from zero. So this condition says zero is an isolated singular point. Does not exclude that some points far away are also singular points. But in this example, we have only one singular point over total space c to the power 2. So Milner vibration, what we do is very simple. We draw a ball around the singular point. So it's a ball of some radius in C2 in our example of some radius r. And if we wish to do a local study, we take a small ball. In the picture, let's assume this is a small ball. Small should be such that what happens inside this picture is the following, that when I take the nearby fiber, f equal to t, and t sits in this disk minus the origin, so d star is the disk minus the origin, of some small radius r, the nearby fiber, then this piece here is called Milner fiber. So in formulas, we take the set f equal to t, and we cut this with the ball around zero of some small radius. This is the Milner fiber, and this we denote by f index t. So locally, for each isolated singularity, we get for every t non-zero some smooth space, some manifold. So in our case, what is this manifold? So perhaps we take the advantage that we can try to solve the equation y squared equal to x to the power 3 in C2. So this has a singularity, so perhaps too complicated. So I take this minus t and t non-zero, and in C2. So for instance, we take x to the power 3 minus y squared equal to 1. So I quickly draw this space. This space is a torus minus a disk. I'll let you do yourself to see this. So when we do it in the whole space, this boundary sits at infinity. So it would be a picture that this goes to infinity. But when we cut with the ball, we cut off, and it will be the torus minus the disk. In this example, the equation is not homogeneous, but weighted homogeneous. So that means the difference between small and big does not exist. We can stretch parameters. So when I stretch x by t by some lambda, and y also by some lambda, a power of lambda, then all those conditions stay invariant. By a homogeneous polynomial, if you stretch all variables by the same power of lambda, nothing happens. The whole picture scales only. So you will not introduce extra singularities. Here, you must be careful. You must stretch this by lambda square and the y, so stretching of x, and lambda to the power 3, stretching of y. So when x is stretched by lambda square, then x to the power 3 is stretched by lambda to the power 6. The same happens here. Y square will be stretched by lambda to the power 6. So in this example, we do not have the trouble distinguishing between local and global. So this helps. So now monodromy is what happens if T travels in this disk. So the puncture disk looks like this. So when I take some T, then I can make T travel. And question is, what happens with this picture when T travels around? So in this example, of course, we can compute this. I will do it later. But the general Milner vibration is you take a general polynomial with those conditions. You take balls small enough. I say something more about what it means small enough. A disk also small enough. And you make T travel in that disk around the origin and see what happens with the fiber. The fiber is the ball called Milnor ball cut with nearby fiber. Yeah. This is called the nearby fiber. This is the Milnor ball. And if you do the intersection, you get from the nearby fiber, you get that piece which sits inside the Milnor ball. And if T travels, that piece will travel and will come back to itself. And the problem is to describe precisely how it comes back to itself. And the diffeomorphism which you get by doing this is called geometric monodromy. This is a dangerous notion because then you must have chosen a connection that you can compare nearby fibers. But if we do not work with this precision, we get something defined up to homotopy, and this is still good enough to compute the action in the homology of that nearby fiber, of that local nearby fiber, of that Milnor fiber. So let's do an example. So basic example is x squared plus y squared. This in other coordinates, I prefer again minus y squared. I can write this as x plus y times x minus y. I can choose this as coordinates u and v. So this example is the same as in other coordinates, the example uv. And we study uv equal to t. And I take t equal to 1. If we stretch everything, then I can manage that t is 1. So the solution space of this means u is non-zero and v is non-zero. So the solution space of this is, so when I study uv equal to 1 in C2, this space is a good way is if I know u, I can compute v. So this is the same as C star. If I have a solution uv, if I know u, the only thing I must make sure is u is non-zero. So the nearby fiber is C star. So C star, I can draw it as follows. I can draw this as...
interrupt you?
Yeah.
Yeah, we can't see your screen anymore. I mean, we can, but we're
You
looking
see
at.
the screen anymore?
Yeah, we can't see you anymore. We're just looking at a flickering screen. So maybe there is some that needs to be, I don't know, adjusted.
Yeah. This is our camera. Wait, I try to repair this video settings. This is ah. Mm-hmm.
You see a small arrow next to your camera, and you can select the
Yeah,
appropriate.
I try to do this. Annette, wir haben Probleme wiederum. Die Kamera hat uns ausgestellt. Aber ich kann sie mir die Computerkamera anmachen. You see something?
We see your laptop's camera, your computer's camera, but not the other camera.
This is
yeah.
the,
Okay. We see the board.
ist gut jetzt? Ja, aber wieso kann der diese, ja.
We still see flickering colors. That's all we see on the other
Is this
camera.
better? No, we have less good camera, huh?
Yeah, it's kind of readable. Yeah.
It's readable? Okay,
Yeah.
so the fiber is C-star and
But you can't write below this level. You'll have to move it up. You can't write below this. Yeah, perfect.
Yeah, okay. So C-star, we can draw it as a set of concentric circles. So here is 0, which is excluded. And then we have circles becoming bigger and bigger and bigger. And then we have circles going to infinity. So what is the monodromy when I do uv equal to t and t travels in d star? And this is very basic thing. So if I wish that t travels in C star, what can you see me here also? So what I can do is I can multiply u by e to the power capital T. So and v also. Then uv will be multiplied by e to the power 2i t. So when t runs, I forgot the factor pi here. When t runs in 0, 1, t runs in 0, 1, then this fiber, this t runs in this star around the origin once. And we could compute the monodromy that way. So if we compute the monodromy that way, we get the following. This whole picture turns a half. You see, when t runs to 1, then u goes to minus u, and v goes to minus v. So it is the opposite point. And the bad thing in this monotomy is at infinity, something happens, and near the origin, also something happens. So what we wish to do, we wish to have a monotomy such that near the boundary, nothing happens. So the monotomy should be constructed in such a way that near the boundary, we have no motion. What was this being? So a good model for this is what people call a Dane twist. So instead of working with C star, I think it as a cylinder. I think C star as a cylinder. This circle is a very small one around the origin, and this circle is a very big one at infinity. And the circle in the middle in C star is the circle of vectors of complex numbers of modulus 1. So what does the monotomy? The first model of the monotomy was this goes to the opposite point. So points here travel to the other side. So it's difficult to draw. This line goes to a line on the back. So, but when I do this at infinity, we have the antipodal map, and near zero, we have also the antipodal map. So what happens? I can, instead of doing this, I can do nothing with one of the parameters and multiply the other. I put a factor 2 here, and here I do nothing. Then this change also. We can imagine that near zero, nothing happens. And at infinity, it makes one turn. And what is then the picture of the monotomy? The picture of the monotomy is as follows. We have this, and such a line goes to the following thing. This line goes to the line on the back, but this line on the back is curved in such a way that it does this. So a better picture is we look what happens with this line on the boundary. This line on the boundary becomes the following line. Is called the Dane twist. So the monotomy of this singularity is the Dane twist. This singularity is very special. We do our computation C x, y, and we divide out the ideal spent by the partial derivatives. So that's the ideal spent by x and y. And we compute the dimension of this. And the dimension of this is 1. So this is the smallest possible number, non-zero, for a dimension. So this means this is the smallest possible singularity. And the monotomy in two variables of the smallest possible singularity is a Dane twist.
Can you move the board up a little?
Yeah. Huh? So in this example, the partial derivatives x squared minus y squared is 2x and 2y. So the ideal spent are all polynomials which are non-zero. So the quotient is just the constants. So it has dimension 1 as complex vector space. So this is the smallest possible singularity, and the monotomy of the smallest possible singularity is the Dane twist. In higher dimensions, we can write this cylinder as in another way. We can take the sphere of dimension n, and we can take the tangent vectors of this sphere of length 1. So this picture, I can think this as the tangent vector of length 1 to the circle. And, pardon, of length less equal 1, pardon. So the cylinder is the same as the tangent vectors of length less equal 1 to the circle. And this generalizes. So when I have the sphere, I can do exactly the same. What we do is we send every point that are the tangent vectors of length 0 to the opposite, to the tangent vector of length 0 at the antipodal point. So a tangent vector of length 0, so I draw something but very small, goes to tangent vector of length 0 at the antipodal point. But a tangent vector of big length, what it does, it flows, and if the length is 1, it does not flow, and the amount of flow is length of the tangent vector 1 minus length of tangent vector. So you flow in the direction of the vector over a distance which is 1 minus its length. This is an analytic model of the Dehn twist, and this is what happens in higher dimensions. But we don't discuss this today. So this model has an extension in higher dimensions. And this leads to formulas, and the formulas which appear are called the Picard-Lefschetz formulas. Picard-Lefschetz formulas. Again, when I take more variables, so plus z square, then here I would have a z, and this one stays unchanged. So the quadratic singularity, sum of squares of the variables, makes also in other dimensions that singularity of smallest possible number. By the way, this quotient dimension has a name. It is called Milnor number. Milnor number measures how complicated an isolated singularity is. Milnor number equal to 0 is no singularity. 1 is the quadratic singularity, also called Morse singularity, and higher is more complicated. So in our example, which was on the other board, the Milnor number here, when we do the computation, it is C x y divided out by the ideal x square and y. So the dimension here is 2. So this singularity has Milnor number 2. It is just one above the smallest possible singularity. So a first theorem which I should mention is this algebraic definition of the Milnor number has a topological meaning. So again, we have Cn plus 1 to C, isolated singularity at 0. Then we have the Milnor number mu is C of x0 xn modulo the ideal spanned by the partial derivatives of f. Pardon, the Milnor number is the dimension of this vector space as complex vector space. That is the Milnor number. So this is an algebraic definition of a number. It is a ring modulo an ideal. You have the Milnor number, and then the theorem. Very important is this algebraically defined number. We assume isolated singularity means mu less than plus infinity. So the theorem say mu equals to something related to the fiber. So we take the fiber, then we can compute its homology. We compute the homology in degree n, and mu is the rank of this Z model. So that is a very important connection. It says some algebraically defined numbers is a Betti number. What happens? You can hear me? Okay, I see you again. So this algebraically defined number has geometric meaning. So next theorem is to say something about the homotopy type of the local nearby fiber. So this is homotopic to something. It is homotopic to a wedge of spheres, and the number of spheres involved is exactly this Milnor number mu. It is a wedge of mu n-dimensional spheres. So this is stronger as what we have here. Here we say the homology is this, and here we say the space is homotopic to the wedge of spheres. So I can draw for you the wedge of circles. So a wedge of k circles. So first we draw one circle.
Can you please go about
we draw one circle for k is 1. When we wish to have another, I draw another circle which is tangent at the chosen point. So this is the wedge of 2 circles, the wedge of 3 circles, 4 circles, and so on. So a wedge of spheres is, you think the spheres as equipped with a base point, and you join all those spheres together at their base point. So another way of drawing a wedge of circles is you draw a first circle, a second circle, a third circle, a fourth circle, and so on. And clearly the homology in degree n of such a thing is the number of circles which are wedged together. And this is a stronger statement. This is a stronger statement than saying that the homology has the right value. So Milnor fibers are wedge of circles. So we go back to our example. Our example, the fiber was the torus minus the disk. So you see that this is the wedge of 2 circles. So the Milnor number is 2. The theorem says the Milnor fiber, which is this torus minus the disk, is homotopic to the wedge of 2 circles. So best way to see this is we draw 2 circles. And we fill in first, we fill in this disk. So when I take the torus minus the disk and put back the disk, I get what people call a torus. And now we have this circle and this circle. And the complement of the two circles on the torus is a square. So this complement is a square. Yeah, abstractly, a square. And here we remove a disk, but from the square I can remove a little square. So what I think this boundary, as something like this. And now we can push the inner square to the outer square. But it was the torus. So this point is identified with this point, this was with this. So this makes the first circle. This is the same first circle, and this is the second circle. So in that way, you see explicitly that the Milnor fiber of x cubed minus y squared is, homotopically speaking, the wedge of two circles. So we need to compute the monodromy in this case. So one way we do the method of Frederick Pham. So we do a Frederick Pham computation. And the example is x to the power 3 minus y squared. So Pham this computation for polynomials which are powers of the variables. So typically a Pham polynomial would be this. This would be a Pham polynomial in 3 variables. And here we have a Pham polynomial in 2 variables. So we wish to solve this equal to 1. Here I prefer to put a plus sign here. So I wish to solve this equal to 1. And this computation is in c to the power 2. So when we solve this equation, we can do the following. First, we look all solutions where y is 0. This gives 3 solutions for x that are roots of unity, third roots of unity of 1. So I draw them. These are the solutions corresponding to y equal to 0. And those dots are the third roots of unity solving x to the power 3 equal to 1. Then I can also look at the x equal to 0. So x equal to 0. And if we solve this equation, then I have y squared equal to 1. I have 2 roots of unity, plus and minus 1. They are here. So what I can do this 1, I can write this 1 as s plus 1 minus s. And s is in 0, 1. And now we solve not x to the power 3, we solve x to the power 3 equal to s and y squared equal to 1 minus s. So when I take s equal to 0, then we are on the first case. We have 3 solutions. When I take s equal to 1, we are on the second case. and we have two solutions. And when S travels in the real interval 0, 1, those solutions get connected. So such a solution, y equal to -1, x equal to 0, travels to this solution. So we get this picture. That is, this graph sits inside, this graph sits inside the fiber over 1. The fiber over 1. And it is homotopic to that fiber. Because if you have a general solution of this, then moving the absolute values of the x and y coordinates, you can shrink everything to this. So this picture sits inside the Milnor fiber of that singularity. First, this thing is homotopic in many different ways to the wedge of two circles. When I shrink this line, I get something like this. Wedge of two circles. When I shrink this line, I get something like this, wedge of two circles. And when I shrink this line, also wedge of two circles. So this is in many ways the same as a wedge of two circles. But this is also a good model to compute monodromy, this FAM graph. It's a good way to compute monodromy. So we need to do something more easy. We take the polynomial in one variable, x to the power 3. And we solve the equation x to the power 3 equal to t. So when t is 1, we have the 3 roots of unity. Bing, what is this noise? So, we have the 3 roots of unity. This for t equal to 1. And when t travels around the circle, what happens? This point travels also to next, and this will travel, and this will travel. So what is the monodromy of this equation? Is a cyclic permutation of the 3 roots of unity. So now we have this graph, the FAM graph, and the monodromy is as follows. We have a cyclic permutation of those 3 roots of unity. So what we can imagine, the top one goes to the middle one, goes to the bottom one, and the bottom one goes to the top one. And at the same time, the 2 roots of unity, y square equal to 1, they exchange. So this one travels to this one, and this one travels to this one. So we can analyze what happens with this picture. So I make the picture again. We see 2 cycles, alpha and beta. This is a cycle, go around this triangle. This is a cycle, go around this triangle. So what happens when we do this motion? Then this edge, where goes this edge? This point goes here, and this point goes here. So this edge goes here. Was this right? This goes here and this goes there. So this edge goes there. Yes. So what happens to this cycle? So this top triangle goes to the bottom triangle. This guy goes here. I made a mistake. This one goes here. So it goes to this edge. So edge E goes to edge E dash. So that means the top triangle goes to bottom triangle, but change orientation. So in matrix notation, we have this. And what happens to beta? So the bottom triangle goes to the sum of the two triangles. So let's check what happens. This, when we go around here, so let's see what happens to this edge. This one goes here. This one goes there. So F goes here. What happens to this one? This one goes here. This one goes there. Goes here. So this bottom triangle, it is better to see this as a square. We have vertices. We have 4 vertices that have a square. And so this bottom square goes to the union of those 2 squares. So in matrix notation, this is this. So the monodromy in homology is this matrix.
How do you write the second column?
Yeah. What?
How do you write the second column?
The second column is the image of beta. So I use the homology of our fiber is Z alpha plus Z beta. So alpha and beta are bases. Alpha goes to minus beta. And beta goes to the sum of the cycles alpha and beta. So in matrix notation, alpha goes to minus beta, this is this, and beta goes to alpha plus beta. So this matrix is a very important matrix. So you can compute, if you do this to the power 6, it is the identity matrix. But it would be much better if we could understand this without computation. Also, something what we see here is that the trace of this monodromy, we have the number of variables is n plus 1. The trace is minus 1 to the number of variables. That's true for this matrix. The trace is 1, number of variables is 2, so what I do here is wrong. To the dimension of the fiber, n.
Can we see the board? I can't see the formula. And minus 1 is?
N is 1. So the trace is minus 1 is 1 here. But this is general. So the trace of the homological monodromy of an isolated singularity where the fiber have dimension n is this. You can also say if total space has dimension n plus 1, then you forget this minus. So the trace is equal to plus minus 1. So this has already consequences, but we will come back to this later. First, we wish to understand why this to the power 6 is the identity. So we do this family of singularities. Y square plus a polynomial in one variable. And this polynomial we take as easy as possible to start with. Is y square plus x to the power n plus 1. I prefer to write mu plus 1. So the Milnor number of this singularity is mu. You can see immediately if we do power series and partial derivatives, so y goes away because y is partial derivative, 2y is partial derivative, and x to the power mu is also a partial derivative. So we have c x y modulo x to the power mu and y. So all y's go away, and remaining is x to the power 0, x to the power 1, x to the power 2, up to x to the power mu minus 1. So we have dimension of this space is mu. So this singularity of dimension where the Milnor number is mu. So mu equals to 1. We get y squared plus x squared that we have seen was Milnor number 1. Mu equal to 2. We have the torus case. Milnor number was 2. And this is slightly more general. So we wish to study this singularity. Excuse me, the telephone is running, but don't worry. So, and we know already what are the most simple singularities. So what we can do is we can perturb this is a polynomial with 0 as root with multiplicity mu plus 1. So 0 root of px is mu plus 1. So what I can do is I can replace this polynomial by one which has only simple roots. So in order to study this singularity, we study the following thing. We do x minus 0 times x minus 1 times and so on, x minus mu plus 1. So I hope I have, no, x minus mu. So instead of having mu 1 0 of high multiplicity, we have many zeros of small multiplicity, of multiplicity 1. So in total, we have here mu plus 1 zeros. And we wish to study this equal to t. And what we do is we take t very big. And we take those distance here to be very small. So say the distance is epsilon. So this polynomial, when we multiply, looks like x to the power mu plus 1 plus something which is of epsilon size. So when this t travels around 0, here t travels, t. You could imagine that those are just one point, or that they are many points at small distance. That does not affect the monodromy when we travel far away from this 0. So when we travel this loop, that computes the monodromy of this polynomial, but computes also the monodromy of this polynomial. Why? The homology is something in z coefficients. And when we perturb by epsilon, we perturb this z matrix a little. But if you take a z matrix and perturb it a little, you don't perturb it at all. So this is a good way of computing the monodromy of this singularity. So we travel this loop and we choose this as base point. So if we compute the monodromy around this big loop, then you compute the monodromy. But this big loop is homotopic to the following path. We go around each 0 once. This path is homotopic to the big one.
Can we see the board?
Ah, excuse me.
Also, I interrupt, but we have
I do this with only 3 rules. Then this is the base point. So this big loop is homotopic to this loop.
Okay, we have 5 minutes left.
Yeah, we have
5 minutes left.
Oh, only 5 minutes left. So, but the monodromy around this monodromy, we know how it works. This was the singularity of Milner number 1. And I'm puzzled now. So this is a way of computing the monodromy by making less singularities. But why?
I think you were also going to answer why the monodromy, the matrix, the monodromy raises how identity.
Those should be 2. This picture is okay, but it's 1 point too much.
Okay.
It's okay, but and this matrix we had before is same as we go around 1 and then around the second, but it's the same as going around both. But for some reason, I have 1 critical value too much, but this we so this matrix is product of 2 Picard-Lefschetz transformations. So what happens if you go around a quadratic? Yeah, I made a terrible mistake. Terrible mistake. So we have those points. When we move two together, that makes that in the polynomial, I have a double root. And when I move two together, then I make a double root. So this makes, if I move those two together, I make a singularity of Milnor number 1. So in our example, we have 3 roots, but there are 2 ways of putting together. So this singularity makes a singularity of Milnor number 1. And this, when I put those together, makes a singularity of Milnor number 1. So this altogether tells me that the monodromy we have is a composition of 2 monodromies, but 2 which are very simple. And if we work out in matrix, perhaps I do, it is the monodromy of the quadratic singularity was as follows. If we have this vanishing cycle, and what happens if we see the vanishing cycle goes back to itself. So this is the first one. And a cycle, another cycle, this other cycle which will be wrapped around the vanishing cycle once. So the typical monodromy of a quadratic singularity is like this. The vanishing cycle goes to itself, and each other cycle which intersects this vanishing cycle, in this case we have only 2 cycles and the other one intersects, gets added to it, the vanishing cycle. But the roles are changed. So this matrix is product of 1, 1, 1, composed with the same matrix where we exchange the roles. And here we must be careful. So this will be 1, 1 with a 0 here. So the other one is sent back to itself. But the other one was, here is a sign -1. So this matrix is product of those 2 matrices. And that is the way of computing more complicated monodromies. You perturb the polynomial such that you have easier singularities in the perturbation, and then the total monodromy is the composition of those easy monodromies. So this gives a recipe for computing the monodromy of those singularities. Yeah, and then next step would be how to compute the monodromy of polynomials in 2 variables. So here we have 2 variables, one variable squared and the others more complicated. So FAM could do x to the power a plus y to the power b. Both variables appear, but there are no mixed monomials. Then next difficulty is how to compute monodromies when we have monomials which are mixed. So typical example would be 7 plus x squared y to the power 3 plus y to the power 11. Here we have, this is FAM-like, but here we have somebody, a monomial where both variables appear. So, general statement, the monodromy of a polynomial in 2 variables, a polynomial having an isolated singularity at origin, can be computed in an algorithmic way. Statement 1. Statement 2. For polynomials in 3 variables, it is nowadays still an open problem to compute the integral monodromy for polynomials having an isolated singularity at 0. So for 1 variable, it is cyclic permutation. For 2 variables, it can be reduced to cyclic permutation by manipulations. For 3 variables, there's no algorithm nowadays. We wish to know computer matrix. You can try to know less about the matrix. So I said already, the trace of the matrix is always 1. So that's some information. But more is known. The eigenvalues of a monodromy matrix of an isolated singularity are all roots of unity. So, and to compute those eigenvalues, this can be done by an algorithm. There's an algorithmic way of getting those eigenvalues. But to know the Z homology, it is already by 2 matrices. If you know the eigenvalues, you do not know the conjugacy class. Even if all the eigenvalues are distinct, for the integral matrices, eigenvalues is not enough. This becomes worse and worse in higher rank matrices. So you can compute the eigenvalues, but you cannot compute the conjugacy class. That's an open problem from 3 variables on. I thank you very much.
Thank you for very, very good. Just quickly, any questions? All right, so there may be you. There should be no question. I have one question. So why do you change this sign? So when you write this matrix in the composition, you have 2 matrices.
Why I took composition?
Yeah, first, it's not entirely clear why you took a composition and how you wrote the second one.
No, my mismatch was, can I explain as follows. So we have a family. We have a family about the disk, and there are 2 critical values. So about each point T, there is a smooth fiber. When I go around 1 critical value, then I have moved this smooth fiber back to itself, and near, so this smooth fiber will have a singularity at 1 point. So those pieces, they go back to itself by identity. But which is near the singularity, this goes by some monodromy. And if we have a family with 2 critical values, then you can go around 1 critical value and then around 2nd critical value. And total monodromy is go around both critical values at once. So the first matrix has an identity part and something extra. And the second matrix has also an identity part and something extra. And the general picture is when you have many critical values, you have as many as there are critical values factors. Each factor does something, has identity contributions and has monodromy contributions. And if the critical values correspond to singularities with smallest possible Milnor number, so quadratic singularities, then this matrix looks, such a factor matrix looks like identity, identity, all. So 1. But 1, 1, in this column, there is somebody else. So you have a product of such matrices. All columns are identity columns, and each one has 1 column with something else. But how those stars are distributed depends on the combinatorics from what's going on. So this gives a computational device for the monodromy. As soon as you can split the polynomial in a polynomial having smaller singularities, such that each singularity is a quadratic singularity, and the singularity people call this a Morsification of the singularity. So if you have a Morsification of the singularity, you can compute the monodromy. And that's what I was doing here.
Yeah, somehow this picture reminded me of this picture reminded me somehow of punctured disc and computing the raw representation of the grade group.
Yes, yes, yes. Yeah. Yeah. Okay. Yeah, so sorry for the beginning that we have our equipment. So my wife knows about the equipment and I mishandle it each time. So that's first thing. But second, this topic is a mixture of doing something very little by hand, so and a global theory. So to become familiar with this, you must know both sides. From the global theory, that is beautiful mathematics, and you can do little in general. But polynomials are very cheap. So a polynomial is, so what means the word cheap in mathematics? I say a mathematical object is cheap if you can type it in LaTeX in say in 10 seconds. That's called cheap. So, and you type in something in your computer, say that 1 minute you take for a complicated polynomial, and you have already a problem. So the amount of examples is huge. You do not need big funding for having many examples. It's not like people doing other sciences. They need big funding. So if they wish to study some virus, this is typically things you cannot do at home. But this polynomial, type in your personal computer, everybody can do, and already has a moderate problem. It is rare how much monodromy can be computed in an explicit way. That is very rare. But the smallest possible examples, say this, so this example, x to the power 5 plus y 3 plus z square plus u square plus v square equal to 0, cut with the Milnor ball. That is a sphere, and that is an exotic sphere. That is already something. The name says it is exotic. It is a sphere with a differential structure which is different from the standard one. Therefore, it was called exotic. But you see how cheap it is. This I can type this say in 1 minute, but people can type it much faster. So this is very cheap. So the geometry of polynomials introduces to you in a very cheap way complicated mathematical objects.
Thank you. Okay, so I have more questions. We can thank you once again. Thank you very much.
Thank you for listening.
And yeah, we apologize at the beginning. Everyone for joining. Thank you again.
Bye bye. Anja, bye bye. Beautiful surrounding here. Is this your garden?
No. This is wishful thinking.
Okay. Yeah, bye bye.
Nice to see you. Bye-bye.